Absolute value inequalities. We've talked about absolute value equations. Now we're going to look at absolute value inequalities. Say, for example, we have the absolute value of x is greater than 5. That means my distance is bigger than 5. So we looked at the absolute value of x is equal to 5, and we saw that those were two different values there. But if it has to be greater than 5, that means we can have all kinds of solutions, in fact, infinite solutions that fit this. So take, for example, -6. Well, -6 is definitely a greater distance than 5 away. So -6 would be one of these solutions. The absolute value of -6 would be 6, and that's greater than 5. So our negative numbers that are less than -5 are going to fit in here and make this inequality true. Well, the same is true with my positive numbers. If I have positive numbers greater than 5, they're going to give us a distance that's greater than 5. So any numbers over here all the way up. So when I look at this, I have two different possibilities. They could be over here, the numbers can be over here, and the numbers can be over here. Now, it can be this solution or this solution. And a good way to remember that when we're doing inequalities is we can look at this sign right here. This sign right here, if we're all solved for we've isolated our absolute value, this sign can tell us what kinds of solutions we're looking for. Since the absolute value of x is greater than 5, we can say the absolute value of x is greater than 5, and that's just a little clue that I use. So let's say we have, we're not including our -5 and 5. It's not included in our distance. It actually has to be greater than. It can't be equal to 5. If we wanted to change that and include 5 and -5, all we would have to do is put a little line under here, and that would mean that they are included. So before, I had an open circle, which meant that it didn't include 5 and -5, but if I have this right here, my circle's going to be colored in, which means it includes both 5 and -5. So when we're looking at our solutions, we can write them in an algebraic way. Remember, when we have the absolute value of x is greater or equal to than 5, we have the ors, and so we have x is less than or equal to -5, that's this part right here, or x is greater than or equal to 5, and that's this part right here. So let's look at a less than symbol. So when we have a less than symbol, we have the absolute value of x is less than 3. That means my distance has to be less than 3, whether negative or positive values. So if my distance is less than 3, I know it can be things like 2 or 1.5, but it cannot be like a -5. If I put a -5 in here, the absolute value of -5 is 5, and that's not less than 3. So it's going to be sandwiched in between there. When I have a less than symbol, I can think of it as less than, and I know it's going to be an and problem. So I also could do the same thing right here. Since I have it's less than or equal to 3, and I'm looking at my distances here, so in between here are all my distances that are less than 3. So everything in there. Both of these things have to be true. If I wanted an or equal to, all I would have to do is put an or equal to right here. And then when I do that, I would color in these dots to indicate that it can be equal to 3. My distance can be 3. So when I have a less than right here, and I've isolated my absolute value, I can think of that as a less than. I'm going to have two things that have to be true there. So I'm going to have x has to be greater than -3, or equal to in this case, because I added that little or equal to. But it also has to be less than 3. It can't just be greater than -3, otherwise it'd go all the way over here. It also has to be less than 3. So I have x has to be greater than or equal to -3, and x has to be less than or equal to 3. We're going to make a sandwich to write this equation. When we have an and equation, we can write it with just one x sandwiched between my two values. So I have -3 is less than or equal to x, because x is over here, which is less than or equal to 3, and now I have my x sandwich. Not very tasty, but very handy in algebra. Now let's look. 3x times the absolute value of x minus 5 is greater than 9. So when we're solving this, we can't look at this yet and say, oh, this is greater, so this is great or. We have to isolate the absolute value. So to do that, we're going to do just what we did when we were doing equations. We're going to isolate this, and it's been multiplied by 3, so we're going to undo that. And we can do that by multiplying by 1/3 on both sides, or we can divide by 3. So divided by 3 on both sides, and we have 3 over 3, which is just 1, times the absolute value of x minus 5 is greater than 9 divided by 3, which is just 3. So now that we have this isolated, we can talk about it being great or. Now when we're looking at this, we're kind of looking at the inside there and what that could be. If that inside is bigger than 3, if the inside, the x minus 5, is bigger than 3, then this equation will hold true. That's where one of my answers comes in. So x minus 5, if that's greater than 3, then the absolute value of that will also be greater than 3. Well, what if the negative, if we're talking about the negative of the quantity inside that absolute value? Well, we want that to be less than -3. Now the reason is if we take the value of something that's less, or the absolute value of something that's less than -3, so say -10, and we take that absolute value, that is going to be greater than 3. So the absolute value of -10 is going to be 10, and that's greater than 3. And so we want the negative of this right here. When we're looking at that, we want this quantity to be less than -3. Now, here's another way to look at it, and I actually like to look at it this way, but it's another way to look at this same thing here, because notice my sign is different on both of these. So if I look at my sign over here, and I have just my problem here, I have x minus 5, the absolute value, is greater than 3. I can also think of that as taking the negative inside there. So if I look at the negative over here, and I want that negative to also be greater than 3. So I have the positive, so x plus 5 is greater than 3, and I also have the negative inside there that has to be greater than 3. If I take the negative of whatever this is, that also has to be greater than 3. Then I can multiply both sides by a -1. Now when I do that, if you remember from inequalities, I have to switch that sign. So if I multiply this by a -1, I just have 1 times it, so I just have an x minus 5. I multiply this by a -1, and I have a -3. And notice I've switched the sign. It's not the same as an equation. And just to give you kind of an intuitive understanding, I'll just give you one example. If we have -1 is less than 10, that's true, right? 1's a negative number. And we multiply both sides by -1. On this side, we're going to get a 1, but on this side, we get a -10. Well, we can't just keep the sign like that inequality like that, because we know that -10, any negative number is going to be less than that positive number. So we have to switch the sign in order to make that true. And that's just to sort of give you an intuitive reason why you're switching the sign anytime you multiply or divide by a negative number. Okay, so now we have those two possibilities. We have x plus 5 greater than 3 and x minus 5 less than -3. We can solve both of those, so add a 5 to both sides. Add a 5 to both sides on each of them, and we have x on this side, the -5 and the positive 5 make it 0, is greater than 5 plus 3 is 8, or, great or, we have add a 5 on both sides, and we have -5 plus a 5, that gives me a 0, and then -3 plus a 5 gives me a 2. So we have x is greater than 8, or x is less than 2. Now, if you look at these, you can tell it's going to be an or, because both of those can't be true at the same time. Either of those will make this inequality true. So let's go ahead and look at them. We're going to go ahead and graph them. We have x is greater than 8, and we don't have or equal to. So that means when we do that part, we're going to have an open circle, not colored in. And x has to be greater than 8. So this way on our number line. Or x is less than 2. Again, we don't have the or equal any of those. And so we have an open circle, and x is less than 2. Now I can use a check for my inequality just to kind of double check. You're not checking every value, but I can check an easy value, and I usually choose 0 to check. So I can check 0. 0 is part of my solutions in this case. And so if I put a 0 in there, this inequality should be true. If 0 wasn't part of my solution set, I could still put it in there, but that inequality can't be true if I put it in there. But in this case, 0 is part of my solution set, so it should make this inequality true. So if I take that 0 and I do 0 minus 5 right here, that gives me a negative 5. I take the absolute value of negative 5, which is a positive 5, times 3. That gives me 15. 15 is greater than 9, and my check worked. So let's try another example, a little bit more complicated. I have negative 2 times the absolute value of x minus 4 plus 2 is greater than or equal to negative 8. Now, I can't say with my greater than or equal to sign that that's a great or, because I haven't isolated my absolute value part of my inequality. I also have a negative 8 here. Now, I don't want you to write no solution because you see this negative 8, because right here, we still have to isolate our absolute value. We don't know that we have an absolute value that's greater than a negative just yet. Okay, so what we want to do, same kind of thing, we want to isolate our absolute value part, and we're going to subtract 2 from both sides. After we do that, we have negative 2 times the absolute value of x minus 4 is greater than or equal to negative 8 plus negative 2 is negative 10. Now what we want to do is isolate this, and we want to undo this negative 2 times that. In order to do that, we can either multiply by a negative 1/2 or divide by a negative 2. Either way, we're multiplying and dividing by a negative. And when we do that, we have to remember to switch that sign. It's a really important part about absolute value problems and can really mess you up if you don't do that part. Okay, so we're going to divide by a negative 2. We're going to remember to switch the sign because we're dividing or multiplying by the negative. And so dividing by negative 2 over negative 2 gives me a 1 times the absolute value of x minus 4, or just absolute value of x minus 4. Switching the sign is less than or equal to, and we have negative 10 divided by negative 2, which gives me a positive 5. Now we have solved, well, we haven't solved, we have isolated our absolute value. And now we can look at that and say, oh, that's a less than, so I'm going to have an and problem, a less than problem. So I'm going to be using and in this case. I'm going to have values that have to be true both ways. So I have here 2 different possibilities. I have x minus 4 is going to be less than 5. So if this right here is less than or equal to 5, and I take the absolute value of it, that's also going to be less than or equal to 5. I also have the negative of this I need to look at. So when I have an absolute value, the positive or the negative distance has to be less than 5. So I'm going to look at the negative. A negative x minus 4 is less than or equal to 5, and I can multiply by a negative 1 on both sides just to get rid of this negative right here. And anytime I multiply that by that negative, I need to switch that sign. Now I could go ahead and distribute the negative and solve it that way too. That's another possibility. I like the way that this looks because it really reminds me of my distance. So multiplying by a negative 1, I multiply this by a negative 1, I just get a 1 times that x minus 4, which is just x minus 4. Switching the sign, greater than or equal to, 5 times a negative 1 is just negative 5. And now we are ready to solve for the values of x. So I have x minus 4 is less than or equal to 5, and x minus 4 is greater than or equal to 5. I'm going to go ahead and solve these for x, add 4 to both sides. This makes a 0 right here, and I have a 5 plus 4, which is 9. So I have x is less than or equal to 9. And I have, adding a 4 to both sides, I have a 0 right here, and I have a negative 5 plus 4, which just gives me a negative 1. And I have x is greater than or equal to negative 1. Now I can go ahead and look at the graph of this. Because I have the or equal to's, I know I'm going to have solid dots in here. I know that x can actually be equal to 9 and equal to negative 1. So that's why those are colored in. I know x has to be less than or equal to 9, so that's this way, but it also has to be greater than or equal to negative 1. So both of those things have to be true because of my and because of my solution set right here. So remember, and also means sandwich, and so we can write this as a sandwich solution. So we have x in the middle of our sandwich, and we have negative 1 is less than or equal to, or you could say x is greater than or equal to negative 1. x is also less than or equal to 9. So we have an x sandwich in here. And I'm going to go ahead and show you a little bit more of a formal check. So I see 0 is in my solution set, so it should make this our original inequality true. Here's our original inequality. I rewrote it down here. So if we substituted a 0 in for x, that should make this inequality true. So let's go ahead and check that. So I have a 0 here in for my x, minus 4, that just gives me a negative 4. Absolute value of a negative 4 is going to give me a positive 4 times a negative 2. So I have negative 2 times positive 4, which gives me an 8. Negative 8. And I still have this plus 2 here. That's greater than or equal to negative 8. So then when we do the calculation, we have negative 8 plus 2, which gives me a negative 6. And negative 6 is greater than or equal to negative 8. So yes, my check worked for this one.